Now that we've completed the sigma-only picture in the octahedral point group for ML6 compounds, I want to do the corresponding treatment for ML4 compounds that are in the tetrahedral point group, and of course, just the sigma donor only situation. So if you go to the tetrahedral character table, immediately you notice something about the nature of where these orbitals are positioned. Is they're exactly the same as in the octahedral point group, except now we've dropped the Garada subscripts. So in this point group, the d orbitals correspond again to two different sets. In this particular case, we have T2 and E, and as I already said, they're not corresponding to anything with a point with a center of inversion, because obviously tetrahedral molecules do not have a center of inversion, which is why the G's and U's are not present. And in this particular case, the T2s also correspond to the Px, Y, and Z axes, and the Px and Y and Z orbitals. And then, of course, A1, which is totally symmetric, still has the corresponding S orbitals. So we do the same treatment as we did in octahedral point group, except I'm not going to go through all the details of working this through. But in terms of picking the four vectors in the ligands, if you basically just have the simple tetrahedral picture of ML4, if you effectively pick the four bonding vectors as your sigma projection operators, or sorry, as your sigma generating vectors, what you'll see is in the sigma only picture, you're going to get A1 plus T2, which is why we have them over here for the ligands. So this is the same exact picture as you get when we do the molecular orbital picture of methane. So nothing's changed. Now in the metal, in terms of the metal center, remember these are, if we're talking about 3D orbitals, this would be the 4s, that would be 4p. And we sort of have all the symmetry labels appropriately labeled. And now what's going to happen is you make sigma bonding and anti-bonding interactions. That drives A1 and T2 down in energy. And of course, you get the corresponding anti-bonding orbitals up here. So these are sigma bonding. And you can see that if each of the ligands are donating one lone pair each, that basically gives you 8 sigma bonding electrons, or effectively a bond order that's equal to 4. So that's basically the 4 sigma bonds that you observe in these molecules. Okay, but now what's going to happen is in this sigma only case, what you sort of notice is that you have something else that's going on here, and that is intermediate is the fact that you've got T2 d orbitals, you've got T2 p orbitals, and you've got T2 in your ligand group orbitals. So recall when we saw this before, what that always means for us is that you'll get a T2 bonding interaction, low energy, you get a T2 non-bonding interaction at midpoint in energy, and then a T2 antibonding orbital that's going to be basically antibonding in nature. So in this particular case, these are the sigma bonding orbitals. These are actually the d electrons are going to be sitting in the non-bonding orbital, and then the anti-bonding orbitals are way up here, high in energy, and really out of the picture of what we concern ourselves with. So when you basically draw this picture, there's no match to E, as you can see. So the E's just come marching right over in the MO picture, and the E's in this thing are non-bonding. But the T2s that are also associated with the metal set are also non-bonding in this picture, for the reasons that you have 3 sets of orbitals that have to make 3 molecular orbitals, and the 3 molecular orbitals means that you're going to have bonding, non-bonding, anti-bonding, and the mid-range energies are those there. And then the energy separation between them, between E and T2 is del T. And the simple fact is why are the E's non-bonding? Well, remember the E orbitals or the EG orbitals in the octahedral point group basically consisted of dx squared minus y squared and dz squared. And that is still the same case here. But what's changed is the nature of the point group, because now the sigma bonding axes don't lie along those vectors anymore. They lie in between the vectors that were in the octahedral point group, which is why they have now T2 symmetry. So they actually match up symmetry-wise with basically the XY, the XZ, and the YZ orbitals. And therefore, what's going to happen in controlling the ligand field splitting is very simply stated. The stronger the interaction of the T2 orbitals, the more this splitting will be perturbed. And again, stronger field ligands will basically increase the energy of that splitting upwards, because you're going to only move the T2s with respect to the E set. So unlike the sigma bonding picture in octahedral, it's the T2 orbital set in the tetrahedral field in sigma only that actually moves, and the E's stay fixed in energy. Okay, next up will be describing the pi bonding only picture in octahedral transition metal complexes. Thank you.